less than 10 seconds.
Hi, and welcome to our new Discovery segment. Today we'll be talking about a signal that researchers have detected from what may be the most massive black hole merger yet with gravitational waves. The signal, labeled GW190521, seems to have been generated by a binary black hole merger with unexpected properties. To date, almost every merger detected has involved either two black holes or two neutron stars. But first, let's do a quick review of what gravitational waves are and how they're produced. Anything that has mass and is accelerating will generate gravitational waves. But since the gravitational waves produced on Earth are way too small to be detected, astronomers search for these signals elsewhere in the cosmos. As two massive objects start to inspiral and merge with each other, they cause disturbances in the fabric of space-time. These disturbances propagate outward as waves, traveling at the speed of light. The detection of gravitational waves gave astronomers another way of listening to our universe, with the other being electromagnetic waves. The latest discovery by the LIGO and Virgo collaborations was announced on September 2nd, 2020, but was actually detected on May 21st of 2019. It involved two inspiring black holes of 85 and 66 solar masses, with one solar mass being one mass of the Sun. To identify objects that produce the signal, researchers at the Max Planck Institute for Gravitational Physics produced a numerical simulation or model of this merger, which produced a simulated signal to the one observed by LIGO and Virgo. And that same simulation is in the video that you just watched. Now, the merger created an even more massive black hole of about 142 solar masses, releasing about 8 solar masses worth of energy that spread across the universe in the form of gravitational waves. Now, according to current understanding, stars that could give birth to black holes in the 65 to 130 solar mass range don't collapse, so we don't expect them to form black holes. This is called the mass gap, and it's the gap between the heaviest neutron stars and the lightest black holes. This was discovered by three physicists in 1967 who realized that when the core of a dying star is very heavy, it'll undergo something called a pair instability supernova, and that's an explosion that totally annihilates the star in a matter of seconds, rather than gravitationally collapsing into a black hole. So here's how a pair instability supernova prevents black holes from forming in this mass gap. We know from Einstein in 1905 that mass and energy are equivalent through his famous formula E is equal to mc squared. As the star's core becomes extremely hot, light begins to spontaneously convert photons into electron-positron pairs, a process called pair production. The light's outward radiation pressure was keeping the star's core intact against the inward pull of gravity. So when light spontaneously transforms into matter, the pressure drops, the core shrinks, and it becomes even hotter. This means that the pair production happening in the core actually happens even more. So the core gets more hot, oxygen ignites, causing the star to explode. You can still get black holes forming on the other side of this mass gap, so having masses over 130 solar masses. And that's because the runaway implosion in the star can't be stopped, even by oxygen burning. They continue to collapse and form black holes. But now, with detection of the signal, the heavier of the two black holes in the merger, weighing in the 85 solar masses, is the first so far to be detected in this pair instability mass gap. One proposal to explain how this black hole formed is through something called a higher argon merger, where this black hole could have been formed by a previous merger between two other black holes before merging with the 66 solar mass one. Now, this discovery is exciting because not only does it have astrophysicists around the world scratching their heads, but also because it demonstrates that LIGO can detect signals even from unexpected astrophysical events. Now, if you want to get involved and help LIGO, you can do so from the comfort of your own home. If you head on over to zooniverse.org, and you can pause the video here to copy down that link, they have a citizen science project called Gravity Spy. You'll help scientists classify glitches from the LIGO system, and your data will help train their machine learning algorithms. They've even included the new signal in the data to be processed, so you'll be working on data right at the frontiers of science. And as always, thank you for listening to our new Discovery Science and Research updates. Don't forget to visit us at spacecenter.ca and check out our online resources that our wonderful staff has curated for curious minds and at-home learners just like you. See you next time.